Hey, it's Dr. J, 6.6, solving exponential and log equations. So we will start today with the exponential equations. And we have what's called the same or the like bases property. It's a property that's almost so obvious, I don't know if it even deserves a name or a number. But I'll go ahead and give it to you anyway. The same bases or the like bases property says that if a to the x is equal to a to the y, then x is equal to y. In other words, if both sides of the equation have the same base, then their exponents must be equal. I will spare you the proof, and we will assume that this property is obvious. So, no proof today. Okay. The best way to actually illustrate this property is with an example. 2 to the x is equal to 8. So 8 is 2 to the third power. 2 times 2 times 2 is 8. Therefore, x is equal to 3. So we're using the same base property or the like base property. Both sides have a base of 2. So that's our a. And so x must be equal to y. So the y is 3. So x is equal to 3. Ten to the x is equal to 1,000,000. Well, 1,000,000 is 10 times 10 times 10 times 10 times 10. There are 6 zeros. So that is 10 to the 6th power. And so x is equal to 6. Sometimes we disguise the base so that it's not so obvious that the two sides of the equation have the same base. You might have a problem something like this. Point 2 to the x minus 7 is equal to 5 to the 3x plus 5. We're already getting into the thick of it here. It does not appear that these have the same base. But you have to use a little bit of arithmetic sense. Point 2 is 2/10. Yeah. Using mental math, 2/10. And that's the same as 1/5. 2/10 is equal to 1/5. So I can rewrite this as 1/5 to the x minus 7. And now you see that the two sides both have a base of 5. We're going to need a little bit of manipulation here. One of them is a 1/5, and this one's a 5, so they have to be identical. But that's not too hard to do. You can just do the reciprocal of 1/5. So 5 to the negative 1. And now you'll have identical bases. The bases should match now. They should both be 5. Removing the parentheses from the left-hand side, we just distribute here. We're going to get 5 to the negative x and positive 7. And now you don't have any more parentheses. So using the same base property, you get negative x plus 7 is equal to 3x plus 5. Now, in the first couple examples, you just got x equals 2 or x equals 3 or x equals 6 or whatever it happened to be. In this equation, you're not done yet. You're going to keep going. But, I've been saying this for weeks now, and I'm not sure if you all believe me, but I will never, ever give you an equation that you can't solve. If you can't solve it, I'm not going to put it on the test, right? So it should be something that you have seen in a previous lecture. It should be something that's been demonstrated many, many, many times. You might not think you can solve it when you see the original problem. That's just psychological, right? But once you dig into it and get it down to brass tacks, once you break it down into an equation that you can actually solve, you will be able to solve it. Basic math here, just move the 3x over to the left-hand side. So we're going to get negative 4x plus 7 equals 5. You could take it home from here. It's all yours. Move the negative 7 over to the right-hand side. So you get negative 2. Divide both sides by negative 4. This all sounds familiar? Yeah, this is what we've been doing for months. And then simplify your answer if possible. Negative 2 divided by negative 4 is 1/2, or I would also accept 0.5. Either one. I don't need both, just however you want to write it, 1/2 or 0.5. Personally, I probably would have done 1/2. Yeah. So that is the like bases or the same bases property. We can also use this property for natural exponential e. So the natural exponential, this one's pretty obvious. I have a very difficult time hiding the base from you when it's the natural base. I mean, it's clearly, you see that there's an e on both sides. The main thing is you want to make sure that both sides look like the same base, identical base. So whenever you see the reciprocal, remember reciprocal means negative power. So change that into a negative 5 exponent. Now, I don't know about you, how you feel about this step here. Sometimes people feel like this step is just a leap of faith. So I'll give you something to do to sort of make you feel like it's not just a wish. You can cancel the bases on both sides. It's not required. But if it makes you feel better, if it makes you feel like you actually did this step, I know some people, when they do mathematics, myself included, when I go from one step to the next step to the next step, I like to actually feel what I did. I like to know that I actually took that step and that the step didn't just happen like you're on a treadmill or something. I'll get more into the mechanics of how this works in the next few examples, but for now we're just using the same base property, or the like base property. So now I'm adding 4 to both sides. I know you can all take it from here. Divide by 3, and you get negative 1/3. Okay, so that's it for the honeymoon problems. The problems that are basically given to you like a buffet, right? They're just laid out in front of you, and you don't have to work very hard. You just kind of go down the line and take a little bit of everything, you know. So expect, I don't know, maybe 5 problems like that, maybe 4, maybe 5 problems that are done very straightforward like that. Now they start to get a little tougher. What if the bases are not the same? Well, that's a really good question. What if the bases are not the same? That could happen. In fact, that'll happen now. So I've got something like 2 to the x is 30. And you could try all day, but it is very difficult. It's not impossible, but it's very difficult to rewrite 30 as a power of 2. It's not impossible, but it's very difficult, right? Think about why. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. 2 to the fifth is 32, and look what just happened. So you're never going to get 30. All right? You can get 16, you can get 32. Those would be same bases, base 2, but it's very difficult, almost impossible to actually land exactly on 30. Right? It's going to skip right over it. So we're going to use logarithms. Now you want to use the logarithm associated with the base. Use the specified base. So in this case, the base is specified to be 2. So we're going to put log base 2 on both sides of the equation. In other words, we're going to use the logarithm to solve the exponential. Now, we discussed the properties of logarithms. And so one of those very important properties was the power property, that you could bring the power down to the front. And now you have x times, technically this is being multiplied, log base 2 of 2 is equal to log base 2 of 30. And now use a little bit of mental math. Remember, a logarithm is asking a question. What power of 2 is 2? Well, 2 to the 1. Yeah? 2 to the first power is 2. So this logarithm is equal to 1. You don't really have to write the 1. X times 1 is just x. And so your answer is log base 2 of 30. This is what we call the exact value. I haven't plugged it into a calculator yet to get the approximate value. To approximate, use your calculator. So that'll be log of 30 divided by log of 2. Or if you prefer, you can use the ln. We saw this in section 6.5. You actually have two choices because you've got two buttons on your calculator. I already wrote down log, so I'm going to go ahead and do log of 30 divided by, here, let me just write it down, 1.477121, blah, 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 divided by log of 2, which is 0.30102, and you're going to get approximately 4.9069. If you're not sure how many decimals to do, read the directions. If the directions don't specify, then do 4. 4 is a good, if you're not sure. That's the standard, at least on my Canvas app that I've uploaded for you guys to enter your answers. Some questions have a smaller request. They might ask for 1 or 2 or 3, but 4 is pretty standard. So I might ask for the exact value. I might ask for the approximate value. I might ask for both. You should always be prepared for both. Interesting note. That's what we call hindsight. So we've already solved the problem now, and sometimes I recommend reflecting on a problem that you've just solved and thinking about, how did you solve that problem and what does the answer actually mean, right? So 2 to the x is equal to 30. If you just rewrite into log form, remember the log form? You have your exponential, you have your argument, and you have your base. So the log form is log base arg equals exponent. All right, remember that? Learned about that earlier in the week, maybe last week. Depends when you watch the video. So we have the base. The base is 2. The argument is 30. And the exponent is x. So your answer should, in hindsight, looking back on it, your answer should make some sense in terms of what a logarithm actually means. Right? A logarithm is essentially a question. It's saying what power of 2 is equal to 30. Yeah. Not only that, but now that you've done the problem, you could take this decimal and you could plug it in right here. It's very easy to check. You are allowed a calculator, so take advantage of that. If you plug in your 4.9069 and you put it into your calculator, 2 raise it to the 4.9069 power, you get 30. Yeah. Well, you get 30.000195556. This is what we call approximation error. You can just ignore that. It's close enough to 30. Look, it's 30.00019. This approximation error is insignificant. As soon as you plug it into your calculator, you're going to get a decimal, and that decimal is immediately going to have some error to it. All right, so you'll never get exactly the right answer when you use your calculator. Interesting note, because I have students comment to me occasionally when they're talking to me, they'll say, Dr. Jordan, I thought calculators were exact. And so when I say exact actually means not using the calculator. A calculator is essentially an approximation machine. It's giving you an approximate value, not the exact value. You want to be exact, don't use a calculator. Okay. All right, so we got the basic idea going. Example 6. Let me start being a little bit more precise with my instructions now. Find the exact solution. Three to the 5x plus 4 is equal to 47. Okay, so our base is 3. So we have log base 3 of 3 to the 5x plus 4 is equal to log base 3 of 47. The exponent, 5x plus 4, can come down to the front. Okay. Use parentheses because we have more than one term here. And then whenever you have a log with a base and a matching argument, yeah, the base and the argument are the same, that's always going to be 1. Again, you could read that out to yourself. What power of 3 is equal to 3? Well, 1. 3 to the 1 power is equal to 3. In hindsight, you can just do this now. You can just cross these guys off. Yeah. When something becomes 1, we often call that canceling because it becomes 1. Although the word canceling has 2 different meanings. Sometimes we mean it becomes 1. Sometimes we mean it becomes 0, and we should be careful which version we're talking about. When we're talking about logarithms canceling, what we mean is they become 1. So now you should have just an ordinary equation. You can get rid of the parentheses on the left-hand side. And now solve this equation for x. It's very important that you keep the parentheses around your argument. Because if you don't put parentheses around that 47, you will accidentally subtract the 4 from the 47, and you can't do that. All right. The negative 4 is being subtracted outside of the argument. It's not part of this argument. All right. So don't write it like this, because if you do that, you're going to end up with 43, and that's going to be a mistake. So make sure you keep the 4 outside. Okay, and then you want to divide both sides by 5. And there you go. This is your exact solution. Don't mess with it. If you mess with it, you're going to break it. Don't put it in your calculator either, because I said exact. So I don't want a calculator answer. Find the solution correct to 4 decimal places. come on back. I think I messed up the focus. Come on back to me. Come on down. There we go. Good. All right, so find the solution correct to 4 decimal places. 4 to the negative x over 12 is equal to 5. So you want to use the logarithm associated with the base that you're given. So we're going to use log base 4. Then you're going to bring the exponent down to the front. Technically, it's being multiplied. You want to put a dot there to make sure you don't screw that up. If you don't put the dot, that's okay, as long as in your mind you know that's being multiplied. Now, we could just cancel this out. I'm going to save you a little step here. This is going to become 1. Log base 4 of 4 is going to become 1. So we can cross it out now and save us a little bit of our board space. Okay, now I have a negative 12. I'm going to do something that I rarely ever do. I rarely ever put my negative in the denominator. But this is one of those times where putting the negative in the denominator will make your life a little easier. Now you can solve this equation in 1 step instead of 2 steps. Multiply both sides by negative 12, and these will cancel. Notice on the right-hand side where I'm putting the negative 12. I'm putting it right in front of the logarithm, right in front of the letter L. So on the left-hand side, the negative 12s are canceling. And on the right-hand side, I've got negative 12 log base 4 of 5. Now I want it to be correct to 4 decimal places. So that's going to be negative 12 log of 5 divided by log of 4. Or if you prefer, you can do the ln. It really doesn't matter. I recommend trying it both ways. You should get the same answer either way. Don't split it up into one of them being a log and the other one being a natural ln. Either they're both common or they're both natural, but they have to agree with each other. Why don't I do my calculation over here? Here, I'll use the ln this time just to show you. So let's see. I start with the ln of 5. So ln of 5 is 1.609437, blah, 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 blah. And I put the negative 12 on the outside. Then I do the ln of 4. 1.3869294. Then I multiply the numerator by negative 12. So the numerator times negative 12. So now I have negative 19.31325. You don't need much more than that. Divided by 1.386294. And you're going to get negative 13.9316. And that's your answer, rounded to 4 decimal places. Okay. Sometimes you don't have to do this conversion here. We call this the change of base formula. We learned about that in 6.5. So this was done in 6.5. Sometimes this is not necessary if you get lucky. Solve. Give the exact answer. And then approximate to 4 decimal places. If the problem already involves E, then you don't have to use a change of base formula because you already have a button that does your E or your ln. Yeah, this is a natural base, so you're not going to need to change it into something else. So you will only need the change of base formula if the base is not E and not 10. So if I give you a problem that's E or 10, then you're not going to need the change of base formula. This one is automatically going to be the ln. All right. So you can just solve it directly. If e to the 5x is equal to 18, you don't need a fancy recipe or a fancy formula. This is essentially a free answer. You have one step, and that's to divide both sides by 5. Make sure that you divide after you've done the ln. All right. Now this is very important. I'm not using the change of base formula, so it's not ln 18 and ln of 5. That would be the change of base formula. Right? This is just ln of 18 divided by 5. So you get 0.5781. So that's your approximate answer, and this is your exact answer. So I sometimes will ask for both. Same question. Approximate to, 4 decimal places. I guess technically that's the nearest 10,000th or something, but I just say 4 decimal places. So we've got 10 to the 2x plus 1 is equal to 7. All right. So now we're going to take the common log of both sides. All right. Notice I don't put a base because it's implied to be base 10. I mean, if you want to put base 10 there, you want to write a little tiny 10 there to remind you in your notes that that's 10, by all means do that. On this side, it's already base 10. So that's going to cancel out. Yeah, if I took the log of that side and the log of this side, these would cancel out because it's base 10 already. So I just get 2x plus 1. Yeah. So it's nice. I would go through, if you have the time, and look for all of the problems that either have a 10 or have an E, and those are the ones that are going to be very straightforward in terms of finding your solution. I mean, you still have to do the work. It's just you don't have quite as much mess when you're solving your equation. So now we're going to subtract 1 from both sides. And then we're going to divide by 2. Now, the order of operations is very important. It's always been important. But in this particular section, if you mess up the order of operations, it's going to cause a lot of pain. So this is the exact value. Log 7 in parentheses, then minus 1, and then divided by 2. Okay. Now, to do it on your calculator, you don't need any fancy formulas. You don't need to do any writing down a bunch of decimals. You can just do the entire thing in your calculator. Do the log first, then subtract 1, and then finally divide by 2. So the approximate solution is negative 0.0775. That would be your approximate solution. One more example of solving an exponential, and then we'll switch over to solving logarithms. Now this question is, we're getting very close to the end here. And so this question kind of goes all the way back to the beginning when we were learning about quadratic equations. Yeah. E to the 2x literally translates into e to the x squared. That's what that means. Yeah, I don't know why I wrote it in purple, but whatever. And then you have minus 3. And then e to the x. And then plus 2. I'm going to switch back to my normal high contrast color here. So I don't know about you, but this is a quadratic equation. Yeah. You see it? We call this a quadratic form because it resembles a quadratic equation. See? This is like your x squared, and this is like your x, and this is your constant. So you should be able to factor this. So e to the x times e to the x, well, that's e to the x squared. Just like x times x is x squared, well, e to the x times e to the x is e to the x squared. And then I always ignore the middle number. Look at the last number, 2. So 1 times 2. I want it to be a positive, so I'm going to make these both negative. Negative times a negative is a positive. And then the middle number, I always check the middle to make sure that it comes out to be negative 3. Yeah, and it does. Look, -1 and -2, if you add them, they should give you -3. And now you're going to have e to the x minus 1 equals 0, or e to the x minus 2 equals 0. So e to the x equals 1, or e to the x equals 2. I said round these to 4 decimal places. It turns out that only one of these is a decimal, or requires decimals. That would be the e to the x equals 2. For e to the x equals 1, you just do the ln of 1, which automatically comes out to be 0. So no calculator is required for ln of 1. But for e to the x equals 2, you have ln of 2. You're going to need your calculator. So that's going to be approximately 0.6931. I do want both solutions. So give me the solutions. X is 0, comma, and then 0.6931. Don't put any fancy parentheses or brackets or braces on your answer. This is just a list of 2 possible answers. The comma reads as the word or. So we say x is 0 or x is 0.6931. Okay, that's it for solving exponential equations. I do have a second episode of turning this around and solving logarithmic equations coming next.